So the title of the talk is here, pairing of normalized eigenstates, and here are my collaborators, Debmal Chakravarti, who had been a PhD students in the group, and this work is built on some master's project of an undergraduate student, Amit Ghoshal, who is now pursuing PhD in Tennessee. Okay, so let's start with some preamble. So it has been observed in recent times that strongly correlated D-wave superconductors, so this long name essentially means for all practical purpose curate superconductors for us. So they are robust to impurities. So there had been several works, including some of ours. So I have highlighted this. Now, what we are going to address in this talk today, that can this result be understood in a simple-minded pairing theory like that of Anderson, when you pair up some single particle eigenstate of the underlying effective Hamiltonian. So this effective is very important, and we'll come to that. Okay, now at the outset, I will tell you that such a simple prescription was actually crucial for what was known for Anderson's theorem for S-wave superconductor, and we will probably mention a little bit more about that as we go along. So let's first give you the prescription of how to deal with strongly correlated superconductors, so D-wave superconductors. So the strong correlation is given by U being much greater than T in a Hubbard model. And then what Shubhra already introduced you in this limit of strong correlation, you can write it as a TJ model, where these operators, creation and annihilation operators, are projected creation or annihilation operator, which takes care of the fact that you do not allow any double occupancy due to strong correlation. So one way of handling such strong correlation or implementing such strong correlation is to what is known as Gutzwiller approximation, in which you will renormalize the parameters T and J of the TJ model, and they are dependent on density, and in presence of disorder, they're dependent on the local density. So now when you put this machinery into computer, what was found, and this is the results that Debmal obtained earlier, that the superconducting correlations like superconducting order parameter or superfluid density, they are far more robust to disorder. They almost had no fall as a function of disorder compared to a theory that doesn't take care of strong correlation, which is the red line, which falls rather sharply. Okay, so this is the thing that is known. I mean, this is what happens within some kind of Gutzwiller-Bogoliubov calculation. So our idea is to understand it, I mean, take a relook at it and understand it in a different way, if possible. So again, at the face value, D-wave superconductors seem to be amazingly robust to non-magnetic impurities, at least for disorder up to some range, moderate disorder. I won't tell you now why it is 3 here, but we can talk later. So now in a mean field description, because delta is proportional to TC, so delta being robust means that TC is not affected by disorder, and that is Anderson's theorem at some level. So is there then, is it very tempting to think, is there something like an Anderson's theorem for D-wave superconductors as well? So I will not exactly answer this question right now, and then I will say that rather let's take a little more careful look at what Anderson's theorem says, and this is actually within quotes. This is a very, very carefully drafted theorem. I mean, so this is from Anderson, that as long as the system remains fairly large, no amount of scattering which leaves the substance of metal would not be able to destroy superconductivity. So what is metal here? So metal is the normal state of a BCS Hamiltonian. So now what is not, so that's my definition of normal state, that if you start with the BCS Hamiltonian, suppress delta by hand, what you are left with is just a metal. Right? I mean, this is metal in the sense that depends on what band structure you take. You can take the tight binding model, and that's a metal, free electron gas metal. Okay, so now the question is, what are the normal state of these strongly correlated superconductors that in question? Okay, so now, the way to sort of get to this normal state is you start with bare Hamiltonian that we have already discussed. Then you first do a Gutzwiller theory. I mean, you write the Hamiltonian in terms of TJ with appropriate Gutzwiller factors, and then do a mean field theory, write down an effective Hamiltonian in this form, which has this Hartree-Fock-Bogoliubov transformation, so which has T effective now, which is local quantity, V effective, and the pairing terms, which is just from the Bogoliubov channel. So remember, when I do this, all these effective things have Hartree shift, Fock shift included, as well as all the effects of Gutzwiller factor. So this is rather complex object obtained numerically. So now I will call the normal state the one where I will now suppress it by hand. So this itself is a self-consistent problem just for the fact that this includes self-consistent parameter like density and other stuff. Okay, and yeah, so I'll go on and I'll probably say something more about it later. Now, just a cautionary remark that our normal state is different from their normal state. So what is their normal state? We often say that this is the normal state, meaning when you suppress superconductivity by temperature, the high temperature phase is the normal state. In our language, what we mean by normal state is by some magic, if you could make this D-wave superconductor disappear, what you are left in this red line, that is zero temperature axis, is what we call normal state. This must be kept in mind. So now the fact that one can think of this results from Gutzwiller-Bogoliubov calculations that we had done before, that they can be thought as a pairing of normal state, the hint was there already, and this is part of the paper which was already written, that what we did is we solved the normal state problem. I mean, I defined what is normal state. Then we construct a BDG type Hamiltonian where this is the self-consistent normal state that we write on the diagonal block. And then we put here the solution of the full BDG solution with Gutzwiller, etc., etc. So now if I diagonalize this Hamiltonian, eigensystem of this Hamiltonian, and just once, I mean, no self-consistency, and I can recalculate delta. I mean, that's the part that you do in any BDG calculation. It turns out this recalculated delta and this, they're just exactly identical. If not exactly, they're very, very similar to each other. So that means that if you had taken the correct normal state, then you need no self-consistency. I mean, and if you have a correct delta. So this is a hint. Now, what we did is to build on that and try to see how better we can do by constructing the theory fully. But the implication of what I said just now is sort of obvious, that the effective single particle normal state parameter of the Hamiltonian which entered on the diagonal block, they remain unaffected by pairing. So this is seen by this thing. I mean, you can look up the thing. I mean, this is the full D-wave superconductor solution, and this is just the normal state solution of V effective and T effective spatial profile, and they look nearly identical. And this can also be seen by taking disorder averaging and looking at the distribution of V effective and T effective. Look, I mean, there's some interesting thing that this V effective, I mean, even though I'm taking a box distribution of disorder, the effective disorder looks very different. But we can talk about that, why that is so. So now, okay. So now what we did then to develop the Anderson type pairing theory with this normal state, I spent sufficient time to emphasize what we mean by normal state. Now this Anderson's pairing theory for S-wave superconductor, actually there are 2 points which are very important. One was that one particle problem of electron in impurity potential solved first to obtain what was that time called exact eigenstate, and then which are paired by BCS type effective interaction. So this is crucial that I can decouple the problem into 2 stages. That's very, very important. That was a very important aspect of what Anderson suggested then, which is mentioned here. And another thing is for S-wave superconductor, only pairing between exact eigenstates, time reverse exact eigenstates are kept in the formalism. So now, I mean, I won't give you the details. I mean, with all that I said, you can easily construct this relatively simple job, and this is what Nitin did for his master's thesis, that if you have, so this was the Hamiltonian written in real space, so you apply some kind of unitary transformation which will make it diagonal to this alpha basis. Then you take the pairing term and you write down the same thing in the alpha basis. So you end up with some Hamiltonian, some final Hamiltonian which is like this with a normal state and then the pairing part. So this looks very much like a BCS Hamiltonian, and you solve it exactly in a manner similar to BCS theory. It is, however, a little bit little more involved for technical reasons. And this is how you relate this delta alpha beta. So remember, this is delta alpha beta, unlike carrying just one index, is what is there in S-wave BCS theory, because it's a D wave. So this leaves on bond. And then you, in terms of this exact eigenstates or these normal states which are here, you can relate this delta alpha beta with those in the bond. Okay, so this is the whole formalism. So then you can work out all the details. I mean, okay, so I probably still have a little bit of time. So you can, I mean, so basically, so the point is if you choose the normal state right, you can do magic by pairing them up in a simple-minded theory. So this is, I will rather show it just by looking at one particular observable, which is the off-diagonal long-range order. So this is what I showed you, that in the Gutzwiller theory, it remains pretty flat, whereas without the Gutzwiller, without strong correlation, it falls sharp. So actually in this, I have also included the pairing theory results, which if I expand the view, this is where it is. I mean, the green is the pairing result, pairing of normal state. So they fall almost exactly on top of the full BDG calculation. And in addition, what you can do, even though I said that delta alpha beta depends on all alpha and beta, so it turns out that by choosing the correct normal state, you can get by pairing only a very small fraction of the normal state, which is actually indicated here, that if you want, let's say 95% accuracy, that means the deviation from the actual calculation, if you allow 4%, only 20% states are good enough to pair to get to the final results correct. And then finally, this is exactly what I said, that if you look, I mean, after you solve it self-consistently and find out the profile of delta alpha beta in the eigenspace like alpha beta, so they remain fairly diagonal all the way up to some disorder up to 3. I mean, this is, so this is, I mean, if it was just diagonal, you just need one state. You need a little more state with disorder, but you can still do pretty well with this. So yeah, so I will leave it here and leave the conclusion for you, and then I'll be happy to take up any question. Thank you for it.
So the one question is that when you say normal state, it is always a Fermi liquid for you?
This is a very interesting question, and yeah, okay, I don't have this backup slide. So that is something which is not fully explored, and that's very interesting. So I missed one point to mention. So this question gives me that opportunity. So this normal state is very different from the usual Anderson model eigenstates. Why? So if you think of it the way I described, so even though you started off disorder only on the diagonal, I mean only on the side, but because of the complex feedback of self-consistency, both T effective and V effective gets disordered. That's fine, that's understood. What is very interesting, it turns out that there is a very strong anti-correlation in space of the disorder in V effective and T effective. As you can see, that V effective, wherever this is large, T effective that is small, and vice versa. This is absolutely clear from this figure, I mean, if you take a look at it. So it's a complex problem, like a one-particle Anderson model, but in a disorder that is spatially correlated. So what the nature of the eigenstates are, there are various interesting observations out of this, which we are actually working on. So for example, they appear to have much bigger correlation, localization length compared to the equivalent exact eigenstate model, I mean Anderson model. So there is a gap, soft gap that opens up at the Fermi level, and that is little different. Because there is a repulsive correlation, you might think that that is a Alsular-Aronov gap, or if Frostlowski is very, very strong disorders, but this looks like a different gap. So they are very interesting feature of that state, which are in the process of investigation. But this still works to generate for me the disordered thing, right? Yeah.
Can I ask one short question? So did you allow this pairing to have any other feature other than D-wave?
So it could in principle, yeah, that part I didn't include. So, right, I mean, I probably understand your question, right? I mean, yeah, so the question is, I mean, if you ask me, yes, there are other terms which are generated in presence of disorder, but very small amplitude. Meaning if you ask for what is extended S wave, so I did not allow as such D wave, I just allowed a pairing of this form. Right? So this could have extended S wave or SXY, DXY and all that, and they get generated, but very small. What is very interesting, phase relation, right? So I tell you the answer, and this is where this is very different from Abrikosov-Gorkov theory, And this had always been there. People just didn't notice carefully, in my opinion. I mean, this was there even when we did this BDG calculation long back. So now I have plotted here for you the pairing amplitude on the bond, right? Because this lives on a bond. So now if you look at it, so yellow has a large value and black has a low value. So if I look at a bond, my x direction has yellow, so y direction has black, is exactly the case for a good D wave superconductor. So I think what you are asking is, can I have same color in the X and Y? The answer is never. So the thing is, yes, you can say that you can, like this case, but that is a special case when both are 0. So you do not break that D wave phase relationship ever. But that was there in BDG calculation all along. So this way, it differs quite significantly from what you expect from this Abrikosov-Gorkov theory. And this is where this pairing of exact eigenstate very important, because you will say that, look, I have taken care of disorder only at a first level. When I go for pairing, I don't care because I have no disorder. Right? That's the spirit of Anderson's theorem, or the pairing of exact eigenstate. So the pairing of exact eigenstate is a very nice way, in my opinion, to sort of comprehend these results which had been there. Yeah, this is a very important point. Thanks for asking.